Hello, and evening everybody, and thank you very much for coming. So I'm Clive, and I'm the head of department of engineering science, and I've been doing this job since the 1st of September, so I'm still slightly fresh-faced and wide-eyed, bushy-tailed, and so on and so forth. But I've actually been in the engineering department since 2005, and so I recognise a few familiar faces and, of course, lots of unfamiliar faces, and it's really great that you've come to join us tonight for Alison's talk. I've been asked to say a few words about Alison Noble, who's going to be coming and giving the talk in a second, and I promise I'll keep it brief. Alison was also an undergraduate and a graduate student in the engineering science department in Oxford. She completed her first degree in 1986 and her DPhil in 1989. And she then went off to work for GE for a little bit before returning to Oxford in 1995 as a member of faculty. And I know there are some people here who were taught by Alison. Can you anybody who was taught by Alison? There we go. You see? Oh, that's fantastic. There you go. Alison was made a professor in 2002, and at the time she was the youngest professor and also one of the joint first female professor. I mean, I assume that means there were two female professors at the same time in the department. And in 2011, she was elected to a chair, the Technikos Professor in Biomedical Engineering, which means she was the first female statutory professor in engineering. She's been the director of the IBME, the Institute for Biomedical Engineering, and she's been associate head of MPLS, which is the division within the university that groups together the mathematical, physical, and life sciences. She's a fellow of St Hilda's College and an honorary fellow of Oriel College and St Hugh's. Alison's research combines AI, computer vision, and clinical medicine. And she's working on application of machine learning in ultrasound imaging. And this is a sort of research with a global health impact, and especially with collaborations in India and Africa, looking at multimodal ultrasounds and sonography and applying data science techniques to that. She founded this company, Intelligent Ultrasound, which to commercialize the research, and that was acquired in 2007 by the Medipore Group. And she's won so many awards that I'm not even sure I can list them all. The BMVA, what does BMVA stand for? Thank you, Distinguished Researcher. I won't make you spell out all the acronyms. Gabor Medal, and she was elected a Fellow of the Royal Society in 2018. And as well as this distinguished research, she contributes to leadership across the science and engineering landscape. She does a lot of work for the Royal Society, leading working groups, for example, in privacy-enhancing technologies. She chairs the Data Community of Interest Science Policy Committee. She works on the Industrial Fellowship Joint Panel. And she's also a member of the EPSRC Engineering Technology Board. There's more. But I think I'm just going to jump to the fellowships. Professor Noble is an Ellis Fellow, an MICCAI Fellow, a Fellow of the IET, where we are today, and the Royal Academy of Engineering, and, as I said, a Fellow of the Royal Society. And she received in 2013 an OBE for services to science and engineering in the Queen's Birthday Honours List. So as you can see, we have today a very distinguished speaker, and I hope you will join me in welcoming her to give what will be, I'm sure, a very interesting talk. Thank you.
Thank you very much, Clive, and thank you everyone for coming. Let me get this. So what I'm going to be talking about is, let me go back one, is I gave it the title of Learning to Address Challenges in Ultrasound Imaging. A lot of my research is dealing with ultrasound imaging, and particularly, as I'll go on and speak about, how the advances in artificial intelligence have really changed the way we can think about using an ultrasound device. And the learning reflects the use of machine learning. But I thought I would take a step back because we hear a lot about AI, and I'm going to be using the phrase AI, artificial intelligence, where really in the imaging sense, we're talking about using deep learning-based techniques. But it has been this rapidly changing area. I've got a couple of slides that I'm going to be showing. If you took a snapshot back in about 2019, these are the sorts of conversations people were having. They were talking about AI was appearing. It was one of the applications would be healthcare. You'd be talking about would AI, in the clinical sense, would it be, you would be meeting, your GP would be a robot. Everyone was scared about taking over jobs. There was going to be some commercial advantages in being able to adopt it, but it was only in 2018 you got the first FDA approval of an AI device. So if you think about that being about 2017 through 19, if you now look at then moving on a little bit, very rapidly some of the conversations and some of the literature you would see coming out was starting to change. You would see the value of being able to work with healthcare. AI was now doubling, tripling, expanding rapidly. And you would see the conversation moving about, were we concerned maybe in the future that jobs would be replaced, to now talking about things about, do we trust people being able to accept AI? And this conversation also going on to think about how do we regulate AI in healthcare? Clinicians were starting to think about how would you evaluate AI tools coming into the clinic, and also starting to think about these data governance issues, about a lot of the, we talk about artificial intelligence, it's all built on having healthcare data. If we've got healthcare data, we need to think very carefully about how we deal with the data governance. So these were some of the underpinning things that were happening now about 2022. And then I thought at this time, well, everything will now mature. As engineering, we have emerging technologies. Everything would sort of mature, things would settle down. But then in 2023, we had ChatGPT. So along comes another new technology. So if you think of over the slides I've shown you, there's been this rapid evolution of availability of technologies. And both in academia as well as outside, we're trying to get to grips to how we can understand how to use the technology. When it's healthcare in particular, we've got to be really careful on how we introduce the technology into practice. So where we are today, I think, is reflected in this sort of study. The sorts of things that we think about is about will AI now replace radiologists? If you think about medical imaging, one of the primary areas is in radiology. So will it now be replacing, which is what everyone worried about originally, or will it actually make them better at their job? And the point about this is how good would an algorithm have to be to take over your job is the sort of question people are thinking about. And it's very divided now as to, is using AI a good idea or is it a bad idea? And you can see some quotes here. You've got quotes that say some of the AI techniques are so good, frankly, we ought to be using them. Why are we not using them? There's the real optimists who want to be able to do the adoption. But you've also got the other people who are much more cautious, who say, well, maybe we should think more about it. Maybe we should check what if it's the data that it was trained on was different than the data I'm going to apply it. And because this actually now affects, it's more to do with humans' attitude towards tech rather than necessarily how the tech is performing itself. And this is so it's a very interesting time now, as you now can prove that technology works, the acceptance of it in the real world is very much in the hands of humans. So the sort of state-of-art questions that I'm thinking about now in my research as a technologist, as well as the end users are thinking about, are things that are shown here. For example, if you have an AI model, does it always need to be as good as an expert, or does it need to be better? Some people, in some areas, that will be true, some it will not. Do we understand human skill at performing a task, and hence how fair or meaningful is it to use that as a reference for how AI performs? And also, when we talk about AI, are we thinking about it as an automation tool, or are we thinking about it as assisting a human, or being an instructor, or being a peer? And this is really broadening out now how we think about how we might use AI in practice. So I wanted to sort of just introduce my talk this way, because some of the questions that I now think about in my research are the ones that that are shown there. But of course, what I really want to talk about now is actually, for my research, how we've got to this point. And I'll go back to this last slide and towards the end. So what I'm now going to talk about is really where my research has been. I've worked a lot in medical ultrasound. And if we roll back, maybe even only a decade ago, if you were looking at medical ultrasound, you would be thinking about the medical physics. How do you make images better? How do you make compensate for some of the artifacts? How do you make the transducers better? A lot of the work was looking at applications and how you can, from the clinical point of view, how you could introduce, particularly over the COVID, for example, there's a lot of interest in how you could improve lung imaging. And the other thing that's happened is you've had this miniaturization of technology. The 1998 was the first ultrasound machine that I bought on a grant with a group in Department of Physiology, quite a big cart-based machine. And it's gone all the way from those cart-based machines, as you can see in the top figure, down to having handheld probes that can attach to a phone quite simply. And that means ultrasound's no longer something you will just see in a hospital. It's something that can go out into communities as well. So that sounds all very good, but it's not that straightforward. And there was, in 2019, there was this market research work was done looking at where the change in use of ultrasound was predicted to happen. And it was this movement from thinking about it as a tool that was used in hospitals and taking it into the community. If you look 5 years on, we're not actually where they would like to be in terms of the adoption. But what underpins this particular graph is not the advances in physics, not the advances in the electronics. It's the introduction of how you use AI to make the devices simpler and easier to use. And it's that space that my group's been working in. So if we go back and look at medical ultrasound, it's a complicated process. If you think about, as shown in that figure, it's not about just looking at a screen. You have a transducer in your hand, you move it into response to what you see on the screen. So it's very much human interacting with a device. And it's very non-trivial if you want to try and think about a robot doing this task. It's really hard task. It's because you've got to understand a lot of interactions. I work in fetal imaging. The fetus moves, so you're learning to recognize from these echo patterns what is going on, how to move the probe to get a good picture. It's like having a torch in moving it around in the body. So you have this complex hand-eye coordination, and what we're interested in, if this is so complex, how can we develop solutions to make it easier? And there's sort of two ways you can do this that really can be posed in two settings. One of them is the highly skilled setting, and the other is in what I call the minimally skilled setting. And the highly skilled setting is sometimes called freehand scanning, and that's where you move the probe around like the torch, and you're trying to discover what's inside your object of interest. The other way, and in that case, if you've got freehand scanning, you end up with video. People talk about capturing certain planes, standard planes, which are certain anatomical pictures. And so the image analysis of that then is on those standard planes. The other way you can simplify ultrasound is through simplifying the scanning. And you can see in the other picture how there's a scanning pattern here where you teach someone how to scan in straight lines. And in this particular case, this is a protocol called the 6-step protocol that is used to train people in low and middle income countries in how to do a basic scan that allows you to check a pregnancy. So in this case, for what's called a structured scan, then that means the image analysis is now on non-standard planes in image and video. So it's a very, very different image analysis and video task, and I'll come on to how we approach that. So if I take the second example first, it's that using these structured scans is how we've worked with a number of groups looking at developing solutions that are more suitable for low and middle income settings, where you'd be going for, as you can see in the far figure, a probe and a small little notebook, and you're trying to be able to do assessment of the health of the fetus from that. And we've been involved with 3 international studies that have been looking, as it says at the top, at either doing gestational age estimation. Gestational age estimation is estimating how many weeks pregnant a mother is, or doing triaging. And in triaging, it's when a mother would come to a clinic and you'd want to be able to assess if there was anything of concern, whether there was a risk associated with the pregnancy. So you go through a checklist in that case to check the health of the fetus. And what characterizes all these studies is that we've worked with, as part of large international studies, and for each of them, we've benefited from working with, they were already doing a very large clinical study, a cohort study, where we could access high quality data sets. So in Kenya, there was a study called PRECISE that was looking at women with preeclampsia. The India-based study is a large cohort study called the Garbini study, which is looking at the health of pregnant women in the India context. And then the international study was involving 8 countries around the world who are estimating the gestational age and coming up with new growth charts. And as an engineering group, by associating with studies of this kind and working with clinical groups, we were adding an element of innovation to these studies, but we were also, in all cases, on both the clinical side and ourselves, we had this shared interest and vision that we would like to be able to develop these tools that could go out and be used in the community settings in each of these environments. So that notion of having international collaborations, shared interest, access to data if you're doing machine learning is really important. You have complementary expertise. We can understand the AI. They understand the clinical context of their work. And in both cases, not only were we developing the technology, but we were also doing capacity building on both sides, so sending the engineers over to the countries to understand the clinical context, and some of the clinicians coming back to my lab and understanding how to work with AI tools as well. So as 2 illustrations of this, one of these projects was called Colopus, which was computer-aided low-cost ultrasound system. And this was a project that is with the Garbini study, which is based in Delhi. And they have a very large cohort study where they are looking at coming up with growth charts and also understanding more about pregnancy in the context of the India population. And why that's important is there's a very high number of premature babies in India relative to, say, in the UK. And so they were interested in trying to understand why is that the case, and how understanding that, how you might come up with better ways to have solutions to pregnancy care in those settings. So because they had this large data set, what we worked on with them, first of all, was to come up with designing what we called the Colopus protocol, coming up with this protocol that was easy for their the people who are doing the scans to perform. And essentially, if you follow one of these simple sweep scans, you have this network across the abdomen that's a bit like doing a sparse scan across the whole abdomen that allows you to assess the health of the pregnancy. And so then, given these sweeps, what we were then interested in, what could we use these sweeps for? You can, for example, do simple things like determine whether the baby's breech or not. So that would be whether the head is down or up. That's clearly very important to understand in terms of delivery of the fetus. We were also interested in finding the position of the placenta, because that's another important risk factor. So taking the placenta as an example, one of the things that one of my students developed was developing a way to take that sweep that's shown at the top, the one very much in the low abdomen, and from that come up with a way to segment key structures, in this case the placenta, which is what's shown in green in the movie, and then the blue then is showing the bladder. And what we were interested in here was how low was the placenta. If the placenta is too low, that's a risk factor, and then you would probably do a cesarean for the mother. So here the key was to be able to identify the placenta. And so that little red circle is showing you the lowest point of the placenta. So Alex, who developed this tool, he developed it, and then it was. Then we were interested in, well, if you had a tool of this kind, would it be acceptable to use it in clinical practice? So he went out to our India partners, and they performed what they called a feasibility and usability study of would it be useful to be able to use this ultrasound video color overlay that I just showed you. And so here is, in the image, you can see Alex with one of the participants in the study. And what this particular qualitative study was looking at was, would they be able to determine the position of the placenta from the video? That was in round 1, as it's shown in the figure. Would they prefer to have the object segmented, which is round 2? Would they prefer to have the circle showing you the lower point, as well as the segmentation? That was done in round 3. And would they also like that box, which is the round 4, which highlights the important area? You care about the distance from that as well. And so they designed this study, and then it was taken to different sites in North and South India, who were the collaborators with our India partners. 31 clinicians who were different, had different roles within the healthcare system in India, and went through a qualitative study to get their views on would it be useful in practice. And what we found in this is that overwhelmingly, in their context, this colour overlay would be perceived as an effective risk stratification. You have to bear in mind here they currently don't use ultrasound at all. And they thought they were actually very excited about this as being something that they could train people to use and that would be useful to be assessing the risk. But they also identified some issues with this. There were some what we call non-trivial, non-technical translational issues, which really relate to socio-technical issues in introducing solutions. One in particular to India is what's called the fetal sex determination law, which means that you have to register every scan when you do that you perform on a pregnant woman, and that's a massive barrier in this context. So although you might have a technological solution, that barrier has to be overcome. And then there were the other obvious ones to do with ultrasound device purchase and also maintenance cost as well. And the reason that I show this slide is, although it's not to do with the engineering, it's really to show that you have to think about these issues. You actually should be starting with some of these issues, because there's no point in developing a solution if it could not be used in the environment itself. And what's really nice now is we have this system and also the training of our students that allows them to go all the way through from developing technology to look at some of these issues in adoption. The second example I'm going to show you is associated with the last example, the transnational study, which is image-based gestational age. Very different problem that we looked at. The data, as I mentioned earlier, was from multiple ultrasound sites, and it was actually aimed at developing growth charts, which has nothing to do with what I'm about to talk about, really. But the important thing about this study called Intergrowth was that the quality of data and the study design. It was 5,000 healthy pregnancies from 8 sites and having multiple scans on women throughout the pregnancy, which meant that in every week in pregnancy, we had many examples of instances of the image. This is the biggest study that's ever been done in the world like this. And what it means is that you've got beautiful data to be able to do regression to estimate gestational age at any point in pregnancy. If you were in the UK, you'd get lots of data at in the first trimester, 12 to 14 weeks, at 20 weeks, and maybe at 32 to 34 weeks, but you would have no data in between. The uniqueness of this study is that it was every week, so you can start to think about doing a true regression. And why that matters in the context of low and middle income countries is that women come at any point in pregnancy. They don't come for screening scans. They don't have what we call a dating scan. So they turn up, they're not well, you don't know how many weeks pregnant they are. And so the original idea of this study was to use biometry, which is capture images, measure ellipses on a head or draw a line on the image, and use those measurements as the basis to form a curve. But in doing this study, my colleagues said, well, why are we drawing ellipses? Why are we drawing lines? Isn't all the information just in the image? Can we actually learn how to estimate gestational age from the patterns we see in the ultrasound image? And we all know that machine learning is very good at pattern recognition. So what we decided to look at, and it was really enabled by this beautiful data set, is to see if we could do the regression and estimate gestational age purely from the image and never get the human involved touching the image. So that's what we went about doing. So we were estimating the gestational age, so that's how many week pregnants. We were doing this based on the image alone. We had the data points, 4,233. These were every week in pregnancy from multiple sites, so we got some nice variation in there. And there was this rigorous definition of gestational ground truth, which is called crown rump length, so we also know that value as well. So it's a very well calibrated data set. And then we used some known methods, but the beauty of this study is less the machine learning, it's the beauty of the data set that allowed you to perform this regression. And from that, we could then do the estimation using regression, machine learning-based regression. And so what did we find? What we found that the best model estimates using the approach we had on this data set was very, very accurate. The absolute error of 3 days in the second trimester and 4.3 days in the third trimester, this outperforms current ultrasound-based clinical biometry in gestational age. In other words, it's better than what humans do in clinical practice. This is particularly significant in the third trimester, whereas if you plot a curve, these lines here, you'd see a much bigger scatter later in gestational age. So you think at this point, great, we have a solution. Fantastic. It's accurate. Everyone should love it. They should adopt it. But no, it's accurate, but then you have, how do you trust it? We're now saying, take an image, we'll tell you what the number is. Where they're going, how do I trust the number? Where's that number come from? I want to fit the biometry on that. That's what I've always done for the last 25 years. So there's this real issue that's classic of having a black box that does really, really well. We believe it as engineers, but we've now got to convince the clinical community that this is a sensible thing to do. So what we've done is we've done what we call a human study. We've called the age study. And this is now a study where we ask clinicians to estimate the gestational age in 3 ways. One, give them the image and say, what is the age, what gestational age do you say this is, based on the image. One is that the second time around when you've had a break is to show the image and give them the AI prediction. So give the number and say, what age do you now think it is? And so if you've told them the AI prediction is good, you would hope if they trusted it, they would use the combination of the two to be able to confirm that they were happy or adjust it if they wanted to. And the third one was to have an AI explanation. And the explanation in this case comes from a technique, machine learning, called proto-PNet, which puts a bounding box around the part of the image that was important to the estimator. That's the important thing here. And so if in practice that you would hope that would be associated to the anatomy that was significant at that particular point of brain development in this case, that you would be able to see at this gestational age, but you wouldn't be able to see, say, earlier in pregnancy. So we did this study. You have a certain design strategy of how you present the information. It was 65 images, 5 per classification bin. In other words, we had different gestational ages, and we had 10 participating experts, sonographers who are participating in this study. So what did we find? Well, what we found was this AI advice. In other words, the model predictions, they helped to reduce the mean absolute error in clinicians' estimates, which was good. So in other words, when you gave the AI suggestion of what the result was, that helped the human. But the model explanations didn't actually have too much of effect. There wasn't a statistical significant result. Was that a surprise? Well, in these sorts of experiments, nothing's a surprise. It was what the result was. So then when we delved deeper, the interesting point was that what we found was, well, when the participants who found this, what XAI is the explanations, when they found the explanations, who found them helpful, they improved. So if they trusted the explanation, they improved in the experiments. But the others who never trusted the explanation in the first place, they didn't show any improvement or they got worse. And this is classic human behavior. And it's sometimes called appropriate reliance, is that if participants get used to something and they rely on a model, then they'll do that if they believe it and it's correct. But they ignore extra information if they don't believe it. So this is also an issue that's really quite important when we think about introducing AI methods. We would hope that if they're accurate, they're doing a good job, that they will be used in practice. But in reality, that human conditioning on it and the human belief in their trust in AI is really important. And as we think about introducing systems into the healthcare system, this is one we've really got to understand a lot more, is how do we communicate to clinical professionals how well systems work to ensure that they use them properly rather than they just ignore them. So that's work we've been doing that's been supporting the low and middle income setting. I'm now going to move on to the other area I work in, which is looking at the highly skilled setting. And this is, as I said at the beginning, is when you're moving around, you're moving the probe, you acquire video, and we'll start with thinking about that area. So in this case, as an engineer, we think about supporting using AI to assist you in different ways. You can either do what more classic image analysis, and you can think about how you can support quality assurance and quantification that's shown in the blue box. Or you can also think about how AI might assist you in that ultrasound guidance box there, which is about moving the probe, searching around, and also adjusting and refining. If you look at the literature and where the emphasis is about, it's been very much looking at the blue box there and looking at how you support quality assurance and quantification. And if you look at the success stories that have really happened over the last decade in my area of looking at fetal imaging, it's largely left led to some quite largely solved what we call downstream tasks. Things like biometry. If you want to be able to automatically measure things, you'll see that in commercial systems. And also the ability to automatically find standard planes and be able to check the quality of standard planes as well. And if you look, if you went out, as I did for this slide a year or so ago, there are many companies now which will offer these sorts of tools, the simple quantification and segmentation tools, and there are multiple instances of that. But I wanted to highlight some work that I've done, and it started out as work in my lab, and then went on to a spin out, and it's now in GE machines. And this is the system as it was in 2022. What's happening here is that as the expert captures an image, they don't do anything else. They capture it. What the AI does is it tells you what view it is. It checks the quality of the view. And then if it's high enough quality, it will place it in the checklist, which you can see on the far side. So it allows the person to really focus on just image capture and not the added step of checking things off. And so a study that was done for this in terms of what we call scan completeness, there are 23 different views you have to capture. So you've captured the head, you capture the abdomen, femurs, you look at kidneys, you look at faces. You go through this checklist. On the fetus, it's really difficult to remember what you've captured. So the fact this is automated really takes some cognitive load off. And sometimes you capture too much, sometimes too little. So if you look at the expert agreement for this, compared with the AI supporting you to do this, you find that they perform very similarly. In other words, the AI helps someone as if they had a peer on their shoulder checking things off. Your peer was there with their book checking them off. You've now got the AI assistant supporting you. The other thing is in terms of image quality, which again, if you had someone supporting you saying, yes, your image is good, move on. Now you've got the AI saying your image is good, move on. You can compare the two. And basically it's now reached the level where the AI is as good as having that expert support, which is quite comforting to people. And this is actually now, as I said, in GE systems. But the other thing that perhaps to me is more interesting is it can also help you in workflow. And I have a movie here that I will now play. And what this system turns out to do is it assists you in reducing what I'd call ergonomic load. And you can see the effect here. On the far side, you've got the manual system. And on your right, you've got using the AI assistant. And as you see that in terms of the hand moving, you see that manually you're moving the person's moving their hand a lot more. They're having to do a lot more work to capture everything, more keystrokes. And that's the key thing that the AI assistant does. It's really important because it actually means that you've got less wrist action. And one of the biggest reasons sonographers have time off is because of their problems with their wrist. You note now you also finish more quickly. That person's gone off to get a cup of coffee while the manual system is still going. So that's also the other advantage. You are more efficient in your time. Now, efficiency is a very interesting one because efficiency could mean if your manager would go, great, you can see a few more in a day, or you could say that person can pause and have a rest before they move on. And so now some of this introduction of the AI is also got to think about some of these issues. The value of AI makes you do more work to get, or is it to help the individual, the person in this case, the sonographer? Next thing I'm going to move on to is now think about this whole process overall. And particularly, I was very interested in moving away from doing video analysis, which is what we've just seen, to say, well, can we learn more about why sonography is hard? And if you're going to look at how sonography is hard, if you look at that figure, it means we need to know where people look, how they move the probe, and ideally, why do they do what they do? So what I did in the project was we translated that into a multimodal project where we were recording with a gaze tracker where someone was looking on the screen. We record how they move with an IMU, so we could have a relative movement of the probe. And we asked them to speak aloud. I couldn't put any brain things on the sonographer. It doesn't go well in a hospital setting. So, but the point was to try and extract from the human more about the perceptions of why they do it. Because if you ask them what they do, you get a very different story, so I wanted to measure it. So the key was to measure. So we had a 5-year project. It was a European Research Council project, so I'm a fan of Europe and European funding, to basically go into the clinic, measure everything, which is what we did. What can we learn from that? You can do what we call sonography data science, which we can use this data to find out what people do in practice. So you can look at simple things like how do they spend time on doing different tasks. We can take the eye tracking data and we can look at how they do eye movements alone, tell you what people do. That's not necessarily going to be an assistive technology, but it shows you the power of using gaze alone and eye information in a machine learning solution. And there are unique patterns people use as they look, for example, at a fetal heart versus they look at an abdomen versus they look at a femur. Femur, you go backwards and forwards. Heart, you focus in the center while you move the probe, etc. And we could also look at some things our clinician were interested in, like why do sonographers, where do they look on a standard plane? They're supposed to check certain things. In practice, do they check them? If they move they're trained to look at what we call a second trimester image. The third trimester image is when certain structures start to become less visible. Do they adapt the rules when they look at the third trimester scans? And the answer there is yes, they do. Does that have implications for training people in how to be able to look at third trimester scans was one of the questions. And we could also measure the pupil diameter change. And the pupil diameter change is related to cognitive load. So when people say a task is hard, can we measure it's hard? That was something else we were interested in. The answer is yes, but it's a very, very noisy measurement. Also, we've now got this 20 minutes, 40 minutes of scans. We could see whether there was a standard way that people scanned, were the personal ways of scanning. And we came up with this analysis, large-scale video annotation, which was taking the video and saying what anatomies were they looking at any point in time. And that color-coded picture in the middle is the whole video drawn out in a line, and you can see at the bottom that's time. The colors indicate what anatomy they were looking at. And even from you there, you can see they often start with the red. They're told to start from a structure, which is the brain. And then it can be opportunistic. We've also looked at whether trainees did things differently than those who were experienced people. Experienced people spend less time moving between structures and sometimes study them more. And so just having this tool has allowed us to start to look at skill of sonography as well. And when you've got the different modalities, you can start to put them together. So if you've got video and gaze, you can build what we call prediction models. So you can look at the question, can a computer predict where a sonographer should look? Video and probe allows you to predict how to move the probe. And video and audio allows you to build text descriptions on images as well. I'm going to touch on the first two to show you what we've done. So the reason to look at, which was one of the original motivations for this whole work, was that little green dot is where someone's looking. And previously, if you worked with video alone, you would have all those pixels with all that information and all that confusion, and you'd have to be trying to make sense of it. If you've got the little green dot, it's telling you, for this particular task, what did the human think was important? It's a natural landmark to place there. So by having that, it allows in your machine learning world, it allows you to focus on that point in space. So now think about taking many, many people looking at this particular image and overlooking at multiple tasks. We have a massive training data set of this multimodal data. We can then build a model that says, on average, where experts would look on a given plane. And these architectures here are some of the architectures and publications we've got. I'm not going to go through them for obvious reasons, but the point was we've explored the space of how we can go about doing gaze prediction. And the examples shown here, those hotspots you can see, are examples of gaze points. So experts would typically look at those structures. And what you see is that little green dot, that little green cross, is for this particular video, we've superimposed the hotspots, and the green is where someone was actually looking. So what you see is them flick between them. Those are the important structures, and they will flick between them. And this is true for other planes. So we thought it would be interesting to see if we've got hotspots, is that useful to train people who don't, like yourselves, don't know what you're looking at? Would it be useful to actually have hotspots so that as people scan, they see the hotspots and they're told, focus on those while you learn to scan, focus on those to help you guide. And we performed a study recently to look at that. And the answer, as I've had with other studies, sometimes it helps, sometimes it doesn't. It depends on the view. But importantly, gaze alone is only one of the perceptions you use. So for some of the tasks you use your eyes a lot, and for others you will be using other information as well. So gaze is very useful, the predictions are very useful, but you really need to be thinking about holistically as a whole. For example, in ultrasound, what is the pressure you've applied? Also really matters. So we've learned that. It isn't that gaze alone is sufficient. When we take video and probe information, we're talking about now the video and also the information about the position of the probe. You can ask the question, can you predict where a sonographer should move the probe next? So you're in one position. How do you get to a standard plane, to a particular target plane? That's what we're interested in. There's two ways we've approached this. One we call control parameter prediction methods, and the other landmark retrieval. The control prediction method is when you're at a place, you tell someone how much to rotate the probe, so say 15.4 degrees. So you're treating the human like a robot. So it might work for a robot, and it's the easiest solution, but it's not very useful for a human to say rotate by 15.4. The landmark-based one is much more intuitive to humans. What this says is you have an image, and you show them in a 3D world where that image is in 3D space. You show them where they need to be as a target, and they can use the 3D to be able to move across to another position. And we've demonstrated this for simulator environment. We haven't yet demonstrated for the fetal case because that's a lot more complicated because the fetus is moving. But in terms of understanding that human-tech interaction, it's more likely that that type of solution is more acceptable. And the other thing that we've looked at is putting video, probe, and gaze together. And the reason to do that is that then you're mimicking this action that is really what sonography is about. And if you take that figure B I've got up there, you start with an image and you'll look at it. And based on what you see, you will move the probe. So you move to the probe movement. Having moved the probe movement, you generate a new image. So you look at that one, and then you move the probe. So you go through this relationship of look, move, look, move. And we wanted to be able to model that. And we have the information in multimodal data to be able to do that. So how you do that in machine learning is if you've got lots of that training data, you set up a graph-based connection between that, and you learn how they are connected to each other they share what's called a modality-aware spatial graph. And from that, it allows you to do the dual prediction of both predicting where someone should look and how to move the probe. And what we've shown in this work is by doing what we call estimating both together, the estimation of both gaze and of probe motion is of higher accuracy than if you estimated from the same data, you estimated either gaze or probe information. And this won an award at our top meeting, one of the Young Investigator Awards for one of my researchers a couple of years ago, and also a Best Paper Prize. So those are some of the things we're doing in multimodal. I thought I would end by talking a little bit about what's emerging. And these are some of the problems that we're thinking about now. If we look at healthcare now, or healthcare as it was, what we used to do, and what I talked about, for example, with the global health projects, was where we had multiple sites and we centralized the data, and then we build a machine learning model based on the centralized data. Now the whole world is moving away from that. They're moving from moving from data sharing to providing data access. And if you have data access, your data stays at sites, and then you have to federate across the sites to be able to build a model. And if you take the UK as an example now, that's what the NHS is doing. It's got this, what they call secure data environments, and it means hospital data is now going into what we call SDEs, these secure data environments, and researchers will be able to access the data, but they won't be able to take it to their lab. Massive change in how people do research, evolving slowly, and we need to think about how we build models as a result. And the technique then that you would use in machine learning is to do what we call federated learning. And this allows you to train a model on this multi-source decentralized data where you can't directly have access to the data. And it's all about making sure that from a privacy and legal perspective that you're respecting that it's healthcare data. So if you think about medical imaging, we have a challenge here because you might be wanting to work with maybe up to 10 sites, as suppose you wanted to work with all the sites around the UK, and there will be this high data heterogeneity. So you've got to think about how you now can build these models when you don't have complete information about the data. And there are things like you will have imbalance in the data. You've got to understand how you can build classification models, segmentation models of the sort that I've mentioned. You've got to understand if you do multimodal, as I've shown you, how would we possibly do that if we were trying to now get data across sites? And so we've also got to understand what are the tasks for which this federated analysis is well suited, and also think, as I have shown you for centralized data, these methods have to be trusted by clinicians as well. So we have to rethink everything. So one of the areas, just to show you an example, working with the group in India, we have looked at the class imbalance, federated learning, and so this was the case study where we had fetal ultrasound video, we had lots of data in India, we had less data in the UK. It's highly imbalanced by class, meaning that the fetal anatomies, you have many of the head and cerebellum and heart, but you have much, much less of other structures. So you have a natural imbalance. And so we've been looking at how you can overcome some of this imbalance by modifying some of the federated learning insides, essentially, to be able to compensate for the balance. And it's studies of this kind. In this case, you ended up by correcting for the imbalance, you could end up with a 20% higher classification of the anatomies. Studies of these kinds are ongoing and are going to be very much part of the future. The second one is thinking about how we can do ultrasound AI assistant. So this is taking these large volumes of, these large videos, and there's a lot of redundancy in there. From a clinical point of view, they'd want a summary. So you go from large video, find the key anatomies, write a simple text description about them, automate biometry. And we've now developed a way to be able to do this that was published this year that reduces it from say, gigabytes of data down to just summarizing as essentially a report, a way to navigate through these videos in a way that's a bit like having an assistant beside you doing the annotation of the video. And so that's sort of an area that's also evolving. And finally, we're looking at what's called guided deferral systems. Machine learning today will always give you an answer. So if you want a classification result, it will give you a classification. What's more human-like is if the AI is uncertain, it will defer to the human, and only when it's confident will it give you a classification results. And so we're looking at these guided deferral systems as being a next generation of working between humans and AI. So just to summarize then, it's sort of ultrasound image analysis has come a long way in the decade. It's based very much on the advances, has originally from large-scale data and also using deep learning. And I've shown you the examples going from automating image analysis tasks, thinking about using tools developed as an ultrasound as an accessible technology, and also the multimodal aspect, both allowing us to understand more about sonography as well as develop assisted techniques. And this is all building on the increasing emergence of different techniques coming out of AI. But I think the most important thing is, and I've tried to illustrate, is that ultrasound is now very much interdisciplinary real-world data science. And it's no longer just about the computer science of the algorithms, but we work in large teams, we do team science, and it's great to be in this position now where we can work all the way with clinicians and including with people like psychologists as well to understand the deployment of solutions. So thank you very much. And these are just a few of the people who I've worked with, and I'm very happy to take any questions.